for inviting me to Caltech. It's in fact my first visit to Caltech. Some people don't believe it, but it is true. So it is, late, but I'm very pleased to be here. So thank you once more. Even it's more than just giving a seminar. It's my first visit here. So I was not asked to give a seminar on a precise subject, so I decided to give the seminar on a the title is the evidence for astrophysical black holes, and I thought that it's a good opportunity, because as you could see, to give it here, because as you could see in my abstract, the conclusion is that the only possible evidence, real evidence for the existence of black holes is going to be obtained through detection of gravitational waves. So, but this conclusion was not prepared especially for you. This is a conclusion I've been promoting for many years, and creating a lot of negative reaction among the X-ray community, of which I'm really part scientifically. I'm more scientifically into the X-ray astrophysical community than in the gravitational wave community. But this is what I think is the truth. So even if you don't like my seminar, you will be at least pleased with the conclusion. Of course, since my conclusion, the conclusion, of course, is not just don't be just pleased, but make the effort to detect something in the end, okay? Because with Albert, we have to explain on these committees. He's part of an experiment. I am not, so. But I have to justify, why we're spending all this money, and why we want to spend more money even on LISA. So I discussed this today with Albert. Please detect something. I mean, whatever. I mean, but just something, a signal. That tiny, even tiny, just suspect. But. Okay. So if you talk to an astrophysicist, for example, a member of the program, we are both attending at Santa Barbara, what is the evidence for the existence of black holes in the universe? I'm not talking here about quantum black holes, the evaporating black holes, just macroscopic black holes. Most of the participants would even understand the questions. It's obvious there are black holes everywhere. There are black holes in our galactic center. It's a view of the galactic center in X-rays. And we know the mass of this black hole. There is probably a small black hole in a dwarf galaxy M33, which is our neighbor, but it's much smaller than our galaxy, doesn't have a bulge. And probably there is just an extra binary in the center. There is a giant black hole in the nucleus of a giant elliptical galaxy in M87, which is part of the big cluster Virgo. Your friends trying to detect gravitational waves in Italy, the French Italian experiment is named after this cluster of galaxy, because they were expecting to detect supernovae from the cluster. I'm not going to explain to you what are the prospects of this. Or maybe stop. There are no much prospects for the moment. And then even now so this is just for people who are not astrophysicists, and with the false color, if you are not a specialist, you probably didn't know. This is X-ray, this is optical, this is optical. This is X-ray. So there are even objects that seems to be binary. So we have two black holes, each is accreting matter and producing an X-ray image. And so you see a binary black hole. So black holes everywhere. So what is the question? What is the question I'm trying to ask? So it's good to have some quotation from an authority, and here. Sorry. Okay. The authority here being the Jim Peebles, who I don't remember where, but it's very handy. It says that good science demands that we see positive evidence support of the black hole picture and watch for the credible evidence that the standard picture may not be quite right. So we are looking for the evidence that objects that are called black holes in the center of galaxies and also a binary system that we'll talk about for the moment are real black holes and not something else. And I wrote a paper in 2002, the same year, with two of my colleagues and friends, Abramovich and Gruzniak, which I think is, I mean, the conclusions are correct. They are the conclusion of, roughly the conclusion of my talk today, but it was written giving the impression that we don't believe in the existence of black holes. And then it's a cited paper, but most of the citation I would like to exist, because these are those people who say, you know, we'll show you there are no apparent horizons, so, you know, Abramovich et al. 2002, etc. So I regret the fact that not writing the paper, but writing this one. So I try to correct it. I have almost finished a paper that will appear soon on Astro.ph. It appears in a special issue of a scientific magazine we've never heard about, except for Stan, which is the Compte Rendu de l'Académie des Sciences. But it will be, of course, on the web. And I tried to correct the impression made in this paper. Okay, so what is the possible evidence for the existence of black hole? How can we tell that something is a black hole? Yeah, by the mass. The mass combined sometimes with density. Of course, I will explain to people who. I mean, if all this, what I'm saying is obvious for you, please stop me and I think most of this thing could be obvious to some people at least, but please stop me if you find that I'm going into details in totally uninteresting and obvious. So mass, surface. I mean, the black hole is not supposed to have a surface in the sense of a solid surface. So there's a lot of papers and activity trying to prove or suggest that what is claimed to be black holes have no real surface. I took part of course on such attempts. I will mention that. And finally, gravitational waves. Here I won't say much about it because you know better than I have one question related to that. And okay, so I will start with the mass. Technology plays an enormous role in detecting black holes. This in particular case in the center of the galaxy. Our galaxy, the long-term suspicion that there is a black hole or a very compact dark object, but due to the technique of adaptive optics, which is just illustrated here by a sort of short movie, I think from ESO. There are two groups working on that. One is ESO, French-German, and then there's Hugo Gabers, who's under, I guess, at UCLA doing very similar things. So this adaptive optics allowed the direct detection of stars around the galactic center. The center of the galaxy, there is a radio source called Sagittarius A star. And we now know that it is really the center, the dynamical center of our galaxy. Is also a radio source. And it seems also that it is the place where there is this massive, very massive, dark, compact object. And due to this adaptive optics technique and also some interferometric technique, which I see are combined in this image. There is a star called S2, or in the UCLA nomenclature SO2, but it's the same star. It is on an eccentric orbit around the center, here at the center, a star, and it was first detected in 1992. It's been followed for, on this image, 10 years, but now it is 40 years. It is beautifully illustrated by this movie. These are the orbits of the star around the galactic center, and you can see there was here a star that was on an extremely eccentric orbit, approached and disappeared. And in fact, there was some confusion for some time because the star appeared, disappeared, but in fact, now we know it went and passed very, very close to the black hole and disappeared. So it's not of much use, but this one is sort of a mercury of supermassive black holes, because when we close the orbit even before, then we'll be able to detect general relativistic correction to the orbit of the star. So it is doing the sort of the equivalent of the solar system test of general relativity in the center of the galaxy.
Okay.
This star here is almost at I think it's 2,000 Schwarzschild radian. So this allows determination of the parameter and puts constraint on what is in the center. There's another constraint which is due to radio astronomy, to interferometry, that gives the size of the region in which there is this Sagittarius A star. This is the size of the supposed black hole shadow. I don't like the name shadow because it's not really a shadow, but you see, I mean, this is the dark spot of the black hole. Right? It's called black hole shadow, but of course it's not a shadow. So there is still some way to go, but the constraint is very strong. And if you look at the various constraints on what is in the center of the galaxy, these horizontal lines are the lifetime of a putative stellar cluster that will be there in this region, and because there's still a possibility that there is it's very abstract possibility, but still there's a possibility that there would be there a cluster of dark objects, stellar objects. But then, of course, it would last very very long. So these limits are given by the lifetime of the putative stellar cluster. The galactic center is an X-ray source that shows variability by the usual argument of the time flight time. The region is limited to that, but this, of course, is always questionable. This type of time-scale argument is questionable. The orbit of the S2 gives as far as I mean, you see this is the size and this is the density, gives a point here, so it's limited here, but the strongest limit is given by the motion is determined by interferometry of the relative motion of the galactic center with respect to S2. Knowing the size and this relative motion, which is, not remember, very small, you get this limit here. So if you take the historically proposed alternative to black hole, I'm not going to go through them, fermion balls and things like that. The only two objects that have been proposed that are left is a black hole and a boson star. Boson stars have the advantage of not being invented, especially as an alternative to black hole, because there are many objects now proposed just an alternative to black hole. These boson stars were independently proposed. They were I think TDV was very fascinated by them for reasons I don't remember. And they came back as one of the candidates for the dark matter in the universe. So they're around for completely different reasons. And then somebody realized, I don't know, that they were supposed to be small, but there is a parameter you can fix so that they could be in this place. So there is not much chance now that even if the limits get I don't think the limit can get closer, and the astrophysical limit by electromagnetic observation can get closer to that. You can probably get here, but the boson star cannot be excluded, I think, by electromagnetic observation. The only way of excluding the boson star will be by observation of gravitational waves. I will come back at the end of my talk. Because the signal from a perturbed black hole and a perturbed boson star should be different. There was a recent paper on that. It's been proposed by Scott Hughes several years ago, and then was recently a paper by Berti and Cardozo showing how to tell the difference between a black hole and a boson star by detecting gravitational waves, which in general is not so interesting, because if you exclude the boson star, so what? I mean, for example, in a binary. But in this particular case, this could be interesting. But for other reasons, it would be difficult to detect. So we have more. Just to mention that whatever are these objects, even there is no final proof that they are black holes, we have now many measurements of mass of the black hole in galactic centers. This is the whole sample from various observations. And there is a big mystery that many of you probably heard about. But there seems to be a rather tight correlation between the mass of the central black hole and the velocity dispersion of the bulge of the galaxy. Around the black hole, there is sort of started from a bulge. The mass of the bulge is much higher than the mass of the black hole. So there should be, in fact, the black hole doesn't influence the motion of the star. They are rotating under their own gravity. But if you look at many galaxies and you can determine the velocity dispersion, there's a strict correlation between, rather by astrophysical standards, between the mass of the black hole and the velocity dispersion. Why? This is not the subject of this talk. This is one of the favorite subjects of our program, but in fact, the answer is nobody knows. For models of that's important, this is a black hole. There are no models of saying this is a boson star, for example. I'm not going to continue on this. I will come now to the determination of the presence of black holes in low-mass X-ray binary systems. These systems are interesting because they have various components that are important for the detection, but I'm not going to go into details. As you will see, the mass of the black hole, the central body, the compact body, is determined by observation of the motion of the companion. There is an accretion disk. This hot spot plays also a role in the detection. There is an accretion disk. Inside there is a sort of a transaction flow, which is not a thin accretion disk. And what is in the center is a neutron star or a black hole. And this is very nice because at least in galactic centers you have a black hole and some invented by very clever theorists or less clever theorists object. Here you have a neutron star. We know the neutron star exists. At least we have good, very good evidence. I'm not going to talk about evidence of existence of neutron stars. And of course, the whole groups calculating signal from merging neutron stars. And in fact, we see here I cannot even doubt about the existence. So, the systems that are interested for detection of black holes or determining the mass of the central object are so-called low-mass X-ray binary transients. The transient system, they go into a very luminous explosion. This system here was the brightest X-ray object in the sky when it burst in 70, whatever it was, 74 or 75. This is the burst. This is this transient explosion that lasts weeks or even months in X-ray in optics. And then the system goes in quiescence. And this is very good because we know just from the property from the luminosity it goes to very high luminosity, even sometimes slightly higher than Eddington, that there must be there an X-ray, so there must be a compact object. So we know it's either a neutron star or a black hole. When everything is quiet, we can see, we cannot see, of course, the compact object most of the time, especially if it's a black hole, but we can see the companion. If we are lucky, and this is only one case, it could be even an eclipsing system. And so this is the companion, so the disk, and the compact object sits in the middle of the disk. This is very unusual. This is very high quality detection. You can see the light curve of the companion star that is filling its Roche law, which is therefore deformed. You can model the so-called elliptical deformation, and the red line is the model that depends on the parameter of the system. The dots are the observation points. I'm not sure they're including the error marker columns. In general, the idea is very simple. It uses Kepler law. It's Kepler's helping Einstein. If you know the orbital period, and this is the first thing you need to determine the projected velocity, then by Kepler's law you can obtain something which is called the mass function. It's called what is usually called the mass function. It's the old name from binary astronomy. That is a function of the mass of the normal star and the mass of the X-ray star, X-ray object, neutron star in this case, or neutron star of a black hole. And at the same time is the minimum mass of the compact object. So if you determine the mass function, you have immediately access, practically model independent, because Kepler laws are Kepler laws, and they are not being challenged. You have access to the minimum mass of the compact object. And now, when it's using something that I don't have to spend too much time on that, we know, it is known that the neutron stars have a maximum mass. What it is, it depends. There's a very nice cartoon, and this sign here is of course, reflect our lack of knowledge what is really happening there, and many people tried, and still are trying, some others stopped trying, but are doing more interesting things. But there are very general consideration that date from the early 70s that can be expressed in this formula, in which the maximum mass depends as the inverse square root of the so-called fiducial density. This is the density at which we decide that we know the property of dense matter. So usually it's taken to be the nuclear density. We believe that we know the property of matter at nuclear density. Now neutron star density in the center are higher than the nuclear densities, as predicted by Madden-Zwicky in 1974. And so usually this is put to the nuclear density, and then you obtain something equal to 3, roughly. So that's why it goes among astrophysicists that the maximum mass of a neutron star is 3 solar masses. That in fact, you can push the equation of state and make it, I don't know, 6 or 4 or something like that. But if you take many, there are many, of course, proposals for the equation of state in the neutron star. If you numerical simulation, this is an example of my colleagues from below, you never get much more than 3 solar masses. So usually it's taken that if the mass of the compact object is bigger than 3 solar masses, then it is a black hole, or until recently it was called the black hole candidate. But of course they are not candidates today, they are either black holes or not. And this is the most recent, I think the most recent situation. Clearly in binary system you have 2 types of objects. Below 3 solar masses, one small exception, there are neutron stars. We know there are neutron stars because there are the pulsar, radio pulsars, There are pulsars in the high mass X-ray binaries, low mass X-ray binaries, and of course we know very well also the masses of binary millisecond pulsars. And they are all concentrated around 1.4 solar masses. And then there's a different class of object. Here, there's the question, are they black holes or not? But they're certainly not neutron stars. And even knowing that you are talking about neutron star black holes, you clearly see there are two classes of objects. And these are the black holes in binary system, but it's non-neutron star in binary system. And there is more and more of them now. I don't know, it's probably 20 of them. These are the low mass X-ray binaries. This is the high mass. This is the oldest known black hole is Cygnus X1, which is in a high mass binary. So now it's routine to say it's black holes. If you are not really interested in fundamentals, or you don't care, but from the astrophysical point of view, it's maybe not so important. These are black holes. But some people care, and some people invent, this is just one example, invent alternatives. And this being the young Bacall in 1990 invented so-called Q stars. There are also alternatives to neutron stars that are strange, or more correctly, quark stars, but they are not interesting from this point of view because the maximum mass is less than 2 solar masses, so they are not in competition with them. Q stars are sort of made, if you look closer, they are made like strange stars, but they are made from baryons. And there's big bags of baryons, and there is some effective potential assumed. They are not kept by gravity, but they are kept by these putative strong forces. I mean, not putative forces, but the expression of these strong forces. You can see, if you don't know if something is kept by gravity or by some other forces, you just look at the relation between mass and radius. Strange stars or Q stars have this shape, neutron stars have this shape. This just reflects the forces maintaining this big body together. And there were several papers about Q stars comparing the mass density relation for various hypotheses and comparing them with observed compact bodies in binaries, but in fact it all is reduced to a very simple expression. The maximum mass is simply the inverse square root of the density of the surface. If you are prepared to have at the surface of a body, of this hypothetical body, a very high density, if you, even at p equals 0, which is I think quite often not understood by astrophysicists, you can have a very high density, like you have in some type of strange star. You can have an almost nuclear density at the surface. Then the argument, because sometimes you see in astrophysical papers saying you cannot have some strange physics at the surface because at p0 the physics must be normal. The physics here could be normal, but at p equals 0 the density could be very high. So if you are prepared to have a high density, on this diagram this is the nuclear density. If you are prepared to have the surface density, for example, here, then you can have very high masses. And you compare this with two observed objects, and you could have, they could be Q stars, if you are prepared to have these hypothetical stars with densities that would be, the surface density would be very high, but would be still composed of Q matter and not of normal matter at rather low densities, below, for example, the 40. If you are prepared to do that, and I don't see if you are prepared to defend the existence of Q stars, you are prepared to do that, then there's no direct evidence that what is called black holes is not a Q star. Okay, the Q star has never been detected in the lab and probably never will be. But still, you can consider them as not totally ridiculous alternative. If you consider them to be ridiculous, it's rather personal taste than an objective statement. Especially that, you know, they are not models of rotating Q stars, and I don't think it's a good subject for a PhD or anything, but they could be as high as 12 solar masses, and then you could argue that some of the black hole candidates are, in fact, Q stars. So it would be good to have an evidence that these so-called black holes don't have a surface, in the sense of solid surface. And the principle of the detection you can be described in long equations, and it's complicated, and you write things about capacities, etc. But the principle is very simple. If you have a bomb that falls into a black hole, and the burning time is much bigger than the photon, you will never see the explosion. But if the bomb stops at the surface of a star, for example, a star, then you will see the explosion. So this is the way of seeing the difference astrophysically, of course not by throwing bomb onto black holes, but by observing the same quiescent low mass anomalies, on the condition that the structure of the accretion flow is composed from a normal accretion disk and what is called an ADAF, which is an advection-dominated flow, which is characterized by one main property, that the radiative cooling time is much longer than the inflow time. So you have this very hot gas falling onto a compact body, but it cannot cool by radiation. So if the center is a black hole, all the gas and the heat will be swallowed by the black hole, and there will be sort of a deficit of energy. Whereas when you have a surface, even if the flow cannot cool, the heat will be radiated from the surface. So there should be a difference, observe the difference between black holes or black holes and systems, object with surface. Okay, I'm not going to talk about the equation because it's not so important. One thing that is important in what I will show at the moment, that the model, because it is an argument which is model dependent, is that the distribution of the accretion rate, mass per unit time that is accreted onto the black hole as a function of the radius is not constant. It is decreasing in the disk. The disk is not in equilibrium, that's why it got into outburst. And then in the other, it is constant. So the value of the accretion rate is constant and is determined by this truncation radius that I don't have time to go into details, but depends on the orbital peak. So this is important to remember that the accretion going onto the surface of the sun here depends on the orbital radius. And by comparing, by observing quiescent black hole and neutron star system, you can tell the difference. And this is a beautiful NASA cartoon, and you see the difference. Okay, it's a cartoon, but it been published some 10 years ago after the first time of this observation. This is an illustration of the fact that when you observe neutron star and black holes in quiescent low mass extraplanet, you see a difference. Okay, how do you see the difference? Because of course this is a cartoon, and this is the latest version of that. So the ADAF model doesn't say that in general black holes are fainter than neutron stars. It says if they accrete at the same rate, then black holes should be fainter. And that's why I pointed out that the accretion rate in this model depends on the radius, it depends on the orbital peak. So now if you plot the luminosity as a function of the orbital period, you see clearly that there's a difference between black holes and neutron stars. neutron stars are always for the given optical period higher than they are brighter than black holes. So this could be considered as the final evidence. Clearly, at least model dependent, but you could say it's only weakly model. Black holes are really fainter than neutron stars. These are millisecond pulsars. I don't think there are any system here, but it's another story. So this has been considered and announced as an evidence. Is it really an evidence? It is sort of an evidence. I mean, go to the right direction and you see, once more you see two classes of objects. It just happened that one are neutron stars, the other are the presumed black holes. But of course there are problems. I'm not going through details of the problems. If you look at the model, the difference should be much bigger. There is a difference, but it should be 10 to 100 times bigger. So in fact, the problem is not with black holes. The black holes are pretty like the model predicts, but the neutron stars are fainter. They should be brighter. So here is a problem with neutron stars. There were some questions, are X-ray emitted from the black hole vicinity? Because there's not only a black hole, there's also the secondary. This could be excluded. The alternative. They are really, we know that they are X-ray emitted from accretion of the black hole. Do X-ray represent the total luminosity emitted in the black hole neutron star? The answer I will show in a moment is probably yes. Are the X-rays emitted by accretion? Could be that they are emitted from the, not through accretion, but for example from nuclear burning at the surface of neutron star. This is a serious alternative. Not from the surface, not from nuclear burning in the black hole. But then if X-rays from neutron star come from nuclear burning in the crust of the neutron star, then what are we comparing with? I mean, is the comparison meaningful or not? That's why, even if it looks very nice and still confirmed, and even if people who don't like the other model are trying to find objects, and one of the putative objects was they're supposed to contradict this, it is still valid, but it's not really it is an astrophysical evidence. It is okay, but it's not final. I'm not going to go into details of what are the proposed solutions. The neutron stars could be fainter because not all the matter would be accreted but would be ejected by the proper effect if the neutrons are magnetized. Some of them are, some of them there's no evidence that they are, so this is still being discussed. And there's no, in many cases, there's no direct evidence from the neutron star problem. Now, this is what I mentioned. Brown, Bilson, and Rutledge proposed that X-rays are, in fact, released from the cooling of core heated by nuclear reaction, deep in the crust during the outburst. So it is just the cooling of the crust. This is a very nice proposal. It has some problems because the spectra do not correspond really to the prediction of the model, and also there's a short-term variability that cannot be accounted by the model or in a very artificial way. But still, this is still being discussed. In fact, the discussion somehow stopped, and people are doing others. Okay, this is just showing that the X-ray are emitted from near the black holes. And there are some other objections. But they're either ad hoc, or they say your picture is not good, but if you look at the details, you see that they imply that black holes have no surface and neutrons have a surface. So there are many alternative models of accretion onto this type of object, but I think they are not of much interest. This also is not so interesting, but no longer interesting. There's now one very serious argument and very simple, that I would like to discuss more in detail, because there are very prestigious people presenting, and one of them is a close friend, so we'll be polemical. So you see from neutron stars so-called X-ray bursts. They are thermonuclear explosion of the fuel. In most of the cases, it is helium. There are some rare cases when it could be something else, but usually it's helium. This is the shape of the light curve, and that quite often they are just going very often. It depends on the accretion rate, depends on the temperature of the core. But it is rather well understood. There is no doubt that it's a thermonuclear explosion of the material accumulated at the surface. So by definition, this cannot be the case of a black hole. And indeed, they are observed from neutron stars. They've never been observed in black hole candidates. So there was Narayan Khaled and Ramesh Narayan, who is a good friend, and other people, and also rather recently, a paper by Narayan, I don't remember whom, and Martin Rees, claiming that this is a final proof that that what we call black holes are really black holes, because since they don't show X-ray bursts, they have no surface. Had they a surface, they would show, if it were object with a surface, they would show X-ray bursts. And the argument is very simple. They took the effort, Jeremy Hyde made the calculation of accretion onto 10 mass objects. And the matter was accumulating and producing X-ray bursts. Therefore, it's the proof that if a 10 solar mass object had a surface, it will produce X-ray bursts. They don't, so they don't have a surface. Okay. What can be the objection? And the objection is very simple, and I'm not sure, I don't understand why they don't want to accept it. We know that this 10 solar mass object cannot be made of normal matter. Because we know that the upper limit is like 3, 4, 5, 6. But 10 solar object cannot be made of normal matter. Now, how we are supposed to know what is happening when matter accretes onto a, let's say, Q star? We know, at least we theoretically know, that there are strange or quark. Oops, I put the hole. There's no surprises. We know that if the matter is in some exotic form, it could be in an equivalent of the color-locked phase that is supposed to exist for strange stars. In such a case, baryons accreting onto the surface will undergo a phase transition, and there will be nothing to there will be no baryons to accumulate to make a burst. No nuclei, no burst. I think the argument is very simple. To that, the answer was in one of the papers by Ramesh student, but this is very artificial because at zero pressure we cannot have a strange set of matter. But of course, strange stars are just a couple of examples. These are models of strange stars that have at the surface a density which is almost as high as the nuclear density. So this is, of course, it's very convincing that they don't show X-ray bursts, but it doesn't show they are not made of some strange type of matter. And to make things more funny, there is, I don't know what experts think, I don't know what you think about this paper if you know it, but there was Horvath and Ludovic. They made a special, they played with the question of strange matter and found the maximum mass going up to, where was it? They got even to 4 or 5 solar masses for a strange star, just by playing with constant. I think nothing wrong with that. Okay, so this is the maximum move. They got foreign assumptions about the black holes. And this is a kind of locked phase. So if you take a black hole candidate with such a mass, it is actually a thing it will never show first because there will be no nuclei. So this argument is not an argument. So the conclusion, because I said I'm going now to almost finish. The arguments about mass are of course a good guide. The argument about the lack of surface are very convincing, but they are not really evidence if you believe that they are alternatives to black holes made of some exotic, abnormal, or whatever matter. And just for sometimes people don't realize the compactness of what is the compactness of the various alternatives to black holes. Of course, the black hole is the most compact. This is the limit which is called the Buchdahl-Bond limit, which in fact was discovered by Karl Schwarzschild in 1916 for the case of constant density. This is for the color. This is the most. I think this is the most compact stretch star. These are the Q stars. These are the neutron stars. And there have been literature proposals of so-called Grava stars. I'm not going to mention, and I had some sympathy for the first paper by Mazur and Motola, but now I think they were completely in the completely wrong direction. If you want to, I don't see why you would like, but if you want to know what I'm thinking about this, I wrote in the paper soon published put on last page what I said about the Grava star. I don't think they deserve all the contempt from the string theorists, but they are not really good candidates. So then I come to just before I get to gravitational waves. There's been a lot in the press, etc. This is the relativistic emission lines observed in some, very rare, but in some object when you suspect in this case in an active galactic nucleus. And this is just what one observes in this, what is the name of in the spectrum of MCG 63015, very strange name. One observes a very large, very wide emission line, ion emission line. And the claim is that the line is so wide that and has so much emissivity towards the black hole, it's emitted practically at the surface of the black hole. And even if you take the maximally rotating Kerr black hole, which is the smallest black hole possible, you still have to emit near the surface. So there was this is just the principle, but of course this is not for this public because everybody knows what the principle is. There are problems with the interpretation. Saying nothing about this observed only in one object. Why is not clear. But the light is supposedly fluorescent, so it's due to irradiation. But one sees sometimes huge variation of the irradiating flux, and the light doesn't move. So it's very, very suspect. And I think the proponent of this model, that it is a relativistic widening, are sort of desperate if you consider that, for example, a model that was explaining the variability and the width had to combine of the ionized reflector from 5 Schwarzschild radii and the neutron reprocessor from beyond 7. When I see such models, I prefer to read some other. It could be, It's not only, I mean, I know this country is problem of intelligent design, but I think if you look at the reality, it's not so intelligent, so it could always happen. I mean, this could be the best argument against intelligent design. But don't repeat it to anyone. The problem is, you said, so is the line so wide? It's not clearly so wide because what is the emission line is decided where the continuum is, and the continuum is not well measured. It is possible that the continuum goes much higher and the line is not as wide as that. This is the total spectrum. This could be the continuum. The line then would be much more narrow. So this is supposed to be one of the arguments in favor of the presence of a curved black hole. Even if there are very intelligent people who could produce a model in which instead of a curved black hole, it was a Schwarzschild black hole for the same light. No, maybe not for this. But I would consider this as an evidence. First, one has to decide where is the continuum, and then second, to explain why you don't see such lines in other objects. There's also another funny thing about this object, but it's not related to the presence of black holes. So, what we are left with are gravitational waves. Of course, you know this is a simulation that you've seen many times. I just put it because it's beautiful. I don't even remember what the author is. So, there are two problems with finding this is a coalescent to black holes. And this is a question I've been asking simulators, and they are busy doing other things. But now that some of the codes are stable, maybe they could do it. I think that if there are two black holes merging, the signal that will be emitted could depend of the nature of the surface that we are perturbing. In one case, we perturb a null surface. In the other case, you perturb a time-like surface. And I think this should make a difference. I don't know if detectable, but in principle, the signal should be different when you perturb a null surface than when you strongly perturb a time-like surface. I was told that it's a very interesting question. That the problem is I knew. But I think this is one way of telling that the objects that are emerging are black holes to be explored. I mean, I think we're on the beginning of numerical relativity. And the second, of course, you know perfectly well. You probably saw it. This is, I think, a picture from Scott Hughes, and it is based on the no-hair theorem. This is also from Scott Hughes. This is based on the ringing of a massive black hole. I'm not going to detail because you've heard it several times. Now it is called, the no-hair theorem was called by Scott, by the way, it's called the two-hair theorem. As they say, the boson cell with a third hair. I don't like the idea, but the idea is that a body that is not a black hole should have a more complicated multipolar structure. A black hole has a trivial multipolar structure. So if there is a compact satellite orbiting the supermassive black hole, the signal, in principle, you can extract from the signal the multipolar structure of the deformed central body and tell whether it's a black hole or not. If it's a black hole, then everything's okay. If it's a black hole, then of course we have to see what will happen. I was very optimistic about this. Before I read, I saw a seminar by Satya Prakash, who claimed that to detect really to make this analysis, there should be at least 10 to the 27 templates. So I'm less optimistic, but we discussed with Steve, and I think they are expert, at least maybe not here, but at least in these buildings, that can reduce it apparently to 10 to the 15. And okay, I would prefer 10 to the 9. I would be really a believer. So this is the type of things I'm saying only when experts when the gravitational wave community and general activity is around. I never say this when the astrophysicist because they introduce this to him. So I really think that the final proof of the existence of black holes systems with horizon, even horizon, will come from the detection of gravitational waves, and I hope for all of us in the near future. So you know what these things are. Maybe you don't know what this is. You don't. And this was what I did. Thank you very much. Lines of observation. The line is okay. Some people put some lines to ease the sort of detecting of the two populations. But in fact, no. The line I put it in fact for myself, and I think in the paper I explained that this is related to the model, and it is not supposed to separate the two populations. It's not supposed to. In fact, people are making statistical tests. They are not preoccupied with the models, and they just find, are there really two populations? And in fact, their line is somewhere here, okay? And then they find statistically there are two different populations.
So if you say, draw me a line, an arbitrary angle that statistically divides this population, there is such a line. It's not just.
I think the line. No, there's no line that divides like the population. If you color it the same way, of course, there is no difference. There's no difference.
One going like this through that black upper limit.
Yeah, but this is not the question we are asking. We are not asking about two populations of unknown objects. Okay, we know that one class of object has a surface. The other we don't know. Let's say we don't know. Is there a difference at a given period? This is something that's been not clear. This argument was used without plotting it's a function of orbital period. Because the argument is not that the two classes have different luminosities. The different luminosity is for the same accretion rate. Okay? It's simply the difference in the efficiency. You have the same m dot, but then it's multiplied by the same efficiency. In one case it's 0.1, in the other is 10 to the minus 3, for example. And this clearly, so you should look at each orbital period if there is a difference. This is the real test.
Bimodal.
Yeah. And so, but I'm not claiming. It is amazing because there's been, when this was first drawn, and I was in fact the first to propose to do it in function of orbital period, I had 3 objects here and 4 objects here. And then you can say, okay, what are we talking about? And there was no coincidence. I think there was this object, and this object, and I think this guy and these 2 guys. So there was really nothing to compare with. Now you have, in this range you have a lot of, a lot. By the standard of the sample, a lot. And this is a new guy. We don't know its orbital period. We know it must be very compact, so it must be below 1 hour. And we know an upper limit, but people claim, oh, this is as faint as black holes. Is for example, and we know it's a neutron star, so because it's shown burst. So this is a counterexample. So I put it just here, assuming the worst possibility, because it could be here. So then of course it's not a problem. I put it here, and I don't see any problem. Now, if one day one found something this neutron star being here, is this really a problem? I'm not sure, because I don't believe this is to be a final argument. It's just the NASA cartoon is very beautiful, but it's just a cartoon.
It's a generalization of that. Roughly speaking, we've been given 2 possibilities in a very differently weighted way: black holes and everything else. Everything else consists. As far apart, once you give up neutron stars, you have primarily a bunch of theoretical caricatures
That's true.
that you use as they can't possibly be. TD's boson stars were not at all meant to be, and I think were not realistic models.
No, it's
or now. And the other, then you could say, well, if you want a model that's not a black hole, and then I'll give, if you let me have arbitrarily distant properties for that model, it could work like this intelligent design one. But so just to sort of condense the wave function, is there any viable, even remotely viable model that is not an X, that is not a black hole, that you could think of this at this point? I think I know your answer, but
Yeah, no, I don't. Yeah, I don't. I mean, you should know better because it's you're one of the guilty parties. You know.
well, I mean,
Yes,
I
yeah,
have my own bias.
Yeah, but when I have look at not at AstroPH but at GR whatever HC etc. and I see paper there, I think everything is possible. I mean it's.
I do.
I mean, okay. I can tell you. I don't know if you saw. There was there's a guy from South Africa called Violier who invented the fermion balls, and now he said the gravitar stars, they have a problem because what's inside, you know, the inside is a de Sitter with you know, it's with an equation of state p minus rho, and he said this is supposed to be universal, but the cosmological constant that you can get from this de Sitter depends on the mass of what is universal. So I say I have something better. What is better? It's Borde-Infeld phantom as an interior of the star. So is it viable? It's a question what you assume is viable, but you know, as you see, there are so many theories that in which you have phantoms and they are supposed to be okay, and the tachyons, you know, are pursuing phantoms or the opposite. So astrophysicists, you know, they don't. Normal astrophysicists, I'm not a normal astrophysicist, they don't go to these pages. They're just content with AstroPH, even if some of these guys, they put this stuff in AstroPH. No, but sometimes this guy put it on AstroPH to scare astrophysicists. But astrophysicists cannot understand, they don't know what a phantom is. So, and so I don't know, Stan. I don't know what, I mean, you should tell me, are there viable alternatives to black holes?
I see papers that say gravitar. I've yet to see any sense of that, but that's me. I mean, so.
Yeah, I know, but so it depends what you think by what is viable.
Is there any plausible story people make in favor of boson stars, like they could form this way in the early universe, and they would have? I don't know anything about what it is.
I think this.
What prevents it from collapsing?
They are Bose condensate. Okay, and you can arrange the constant. There is, I don't remember now because I'm not very familiar. You probably know, Lee.
Yeah, there's a potential one,
Yes.
like the uncertainty principle or something.
Yeah. Yeah, they're very interesting. You know, mathematically, they don't have an equation of state, etc. But
Well, you could provide that. You potential any way you want.
yeah, they were designed to be small, and I don't think that I haven't heard anything about them being produced in the early universe. But you know, if you say Bose condensate or something, I bet you there's at least 100 articles in JRQC it's justifying it. I'm simply not sure it's worth reading. But they were not designed to be an alternative to black holes. They were at the beginning they were small. There was this paper by Ruffini and Bonazzola in, I don't know, 50 years ago or something. Yeah, which was very interesting. But it was just as an interesting physical example of different type of matter, etc. And then I don't know why TD got excited about them. I don't remember that. There was one I remember some 15 years ago. There was even an editorial in Nature. Something about boson stars, and they completely disappeared. They reappeared as candidate for dark matter. I think Andrew Liddell is one of the proponent. And then I found them in the article by Schödel et al. About the galactic center. There was this black hole, and there was a boson star, and I said, "Oh, boson star, what is doing here?" And then.
know that, but then just sending the paper saying why you think it's implausible.
But I don't think there's any plausible argument why you should have a 10 to the 6 solar mass black hole in the galactic center. And certainly there's absolutely no plausible argument why you should have a boson star in a binary where the black hole is supposed to be formed through gravitational collapse of, say, a supernova after a supernova. We don't know everything about supernovae, but I don't think it's the best. It's very plausible that during the supernova explosion you have the phase transition from fermions to a boson condensate of whatever type. So this is, I think, I would say this is not viable. I mean, binaries, I think, except for sort of things made of quarks, I think it's all the alternatives is. I mean, it's very naive. You know, it's the argument in the article, even the one that is so nice about the Grava stars. That so the Grava stars have an entropy, very low entropy by design, but they have an entropy 20 orders of magnitude lower than a normal star. They say it's been ejected during the supernova explosion. So it's no. So I think that, to answer your question, there's no viable alternative, but there is no proof that you have to do with you are dealing with systems with no surface. And I think that this is to encourage, you know, the gravitational wave community.
Which takes me to the last question I wanted to ask, which was, you suggested that perturbations of a space-like surface and a time-like surface should be intriguingly different.
Yes.
How would you put together a mass 20? You have to have an equation of state that isn't just nuclear matter. Could you do that numerically?
Sure, I can make up any.
All right.
See? Three solar masses, it's certainly possible with absolutely no problem. I don't think it's scaled with mass. The problem is scaled with mass. You can, from this point of view, you can have one solar mass black hole and one solar mass neutron star. So,
And the other